What if an entire branch of humanity walked the earth, lived, hunted, dreamed, and then disappeared almost without a trace, hidden inside ancient caves, forgotten fossils, and even our own DNA, are clues to a lost chapter of human history that scientists are still struggling to understand. Tonight we're uncovering the incredible story of the lost relatives who nearly vanished from time itself, and what their existence reveals about who we really are. If you enjoy mysterious history, ancient civilizations, and the greatest archaeological discoveries, don't forget to like this video, subscribe to the Lost Branch of Humanity, and join us as we journey into humanity's forgotten past. A narrow beam of light cuts across the darkness of a limestone cave, revealing the faint outline of a bone that has rested untouched for tens of thousands of years. At first glance it appears unremarkable, little different from countless fragments recovered from ancient landscapes across Europe and Asia. Yet beneath its weathered surface lies a story capable of changing humanity's understanding of itself. The bone belongs to someone who is unmistakably human, yet not entirely one of us. It comes from a branch of the human family that flourishes for thousands of generations before quietly disappearing, leaving behind no cities, no written language, no monuments, and almost no memory. Only scattered traces remain buried beneath layers of earth that patiently preserve secrets far longer than civilizations ever could. For most of recorded history, people imagine the human story as a straight line stretching from primitive ancestors toward modern civilization. It is a comforting picture, simple enough to fit neatly into books and classrooms. But the deeper archaeologists dig, and the more carefully geneticists read the code hidden inside ancient bones, the less convincing that simple picture becomes. Humanity does not emerge from a single uninterrupted path. Instead, it resembles an ancient tree whose branches spread outward in unexpected directions. Some flourish for immense spans of time before ending abruptly. Others divide again and again. Only one survives into the present, while countless others vanish so completely that even their names are forever lost. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. The remarkable truth is that modern humans are the last remaining members of a once remarkably diverse family. Today it is impossible to walk across the landscape and meet another kind of human. Every face belongs to the same surviving species, yet for much of prehistory that is not the world our ancestors inhabit. Different human groups roam forests, cross frozen valleys, climb mountains, and follow rivers toward distant horizons. They adapt to climates ranging from warm African savannas to the icy plains that stretch across Ice Age Eurasia. Some possess bodies built for bitter cold, others thrive in tropical environments. Each represents an experiment carried out over hundreds of thousands of years by evolution itself. The evidence for this forgotten diversity emerges only slowly. A jaw discovered in one cave refuses to resemble any known species. A tiny finger bone recovered from another site produces astonishing genetic results. A fragment of skull found decades earlier suddenly gains new significance when compared with modern analytical techniques. Discoveries separated by thousands of kilometers begin fitting together like scattered pieces of an enormous puzzle whose picture remains incomplete. No single explanation fully accounts for every mystery these discoveries reveal. Some fossils fit comfortably into established categories. Others stubbornly resist classification, displaying features that seem to belong to multiple populations at once. Scholars still debate exactly how many distinct human groups once exist, whether boundaries between them should be drawn, and whether some populations deserve recognition as entirely separate species or merely regional variations. Nature rarely follows the tidy categories that people prefer to impose upon it. Long before cities rise beside rivers or kingdoms compete for power, the greatest drama in human history unfolds almost silently. Small communities move with the seasons, tracking migrating animals and gathering edible plants across immense landscapes. Children grow to adulthood without ever seeing a permanent settlement. Fires flicker beneath rock shelters while glaciers advance and retreat across continents. Entire coastlines appear as sea levels fall, only to disappear beneath rising oceans thousands of years later. The world itself refuses to remain still, and every shift demands new forms of adaptation. Survival in this ancient age depends less upon strength than flexibility. Climate transforms repeatedly over hundreds of thousands of years. Warm forests give way to open grasslands. Dry winds replace abundant rainfall. Rivers carve new valleys while others vanish entirely. Animal populations migrate or disappear, forcing human communities to adjust their movements and technologies. Those unable to adapt slowly fade from the archaeological record, leaving only scattered bones and stone tools as testimony that they once existed. What survives in the record suggests that extinction is rarely dramatic. It is seldom a single catastrophic event that erases an entire people overnight. More often, it unfolds gradually. A population becomes isolated. Birth rates decline. Resources grow scarce. Neighboring groups expand into familiar hunting grounds. Genetic diversity decreases generation after generation until recovery becomes increasingly difficult. Eventually, the final members die without realizing they represent the end of a lineage stretching back hundreds of thousands of years. This gradual disappearance explains why so much remains hidden. Bones decay unless extraordinary conditions preserve them. Wooden tools rot away. Clothing made from animal hides leaves almost no trace. Entire campsites vanish beneath sediment carried by rivers over thousands of seasons. Even when evidence survives, it often lies buried beneath cave floors or sealed beneath ancient deposits that remain untouched until modern excavations uncover them. Archaeology therefore resembles listening to a conversation from which nearly every sentence has been erased. For centuries, researchers know only fragments of the story. The first discoveries challenge accepted ideas but fail to overturn them completely. Early interpretations often reflect the assumptions of their own time, imagining ancient humans as crude, unintelligent, or fundamentally inferior. Such conclusions gradually begin to collapse as new evidence accumulates. Sophisticated stone tools appear beside fossil remains. Signs of controlled fire become increasingly common. Careful burials, possible symbolic behavior, and evidence of long-term survival, despite serious injuries, all hint at lives far richer than earlier generations imagine. The greatest transformation arrives not through larger excavations, but through technologies capable of examining details invisible to the human eye. Microscopic wear patterns reveal how stone implements are used. Chemical signatures preserved within teeth reconstruct ancient diets. Isotopes locked inside bones record movements across landscapes. Most astonishing of all, fragments of ancient DNA survive inside exceptionally preserved fossils, allowing scientists to compare genomes separated by tens of thousands of years. Suddenly, the silent bones begin speaking in an entirely new language. Their message is surprising. Humanity is not simply descended from those who come before. Different branches meet separate and sometimes reconnect. The family tree is not composed of cleanly divided lines, but overlapping histories shaped by migration, isolation, adaptation, and occasional encounters. Some vanished populations leave no living descendants. Others disappear physically, while fragments of their genetic legacy continue inside millions of people alive today. Extinction, it turns out, is not always absolute. Standing inside a cave where these discoveries emerge, it becomes easier to appreciate the immense scale of time. Every layer of sediment represents centuries or even millennia. Tiny changes accumulate until entire worlds replace one another. Animals evolve, climates shift, mountains erode, and human populations rise and disappear without leaving monuments to commemorate their existence. The landscape remembers even when memory itself is gone. The mystery of the lost branch of humanity therefore begins not with certainty but with absence. Missing names, missing voices, missing histories. It begins with fragments patiently assembled across generations of scientific work, each discovery illuminating another corner of an ancient family whose full story remains unfinished. Somewhere between the familiar face reflected in a modern mirror and the weathered bones resting beneath cave sediments lies a forgotten chapter that continues to reshape humanity's understanding of its own origins. The journey into that hidden past has only just begun. For most of the last 300,000 years, the Earth is not inhabited by a single kind of human. Instead, it is home to an entire collection of closely related populations, each following its own evolutionary path while sharing a common ancestry that stretches back much further into deep time. If someone could stand upon a high mountain overlooking the continents during the middle of the Ice Age, the world below would not belong exclusively to Homo sapiens. Across vast distances, different branches of humanity occupy forests, river valleys, windswept steppes, rocky coastlines and mountain caves, each adapting to environments that demand different solutions to the same fundamental challenge of survival. This forgotten diversity is perhaps the greatest surprise modern archaeology has uncovered. For generations, scientific illustrations portray evolution as a neat procession of increasingly modern figures walking from left to right. Although memorable, that image hides a far more complicated reality. Evolution does not move like a straight road leading toward a predetermined destination. It behaves more like an intricate river system, constantly dividing into smaller channels, some flowing for immense distances before merging again, while others gradually dry up and disappear. Humanity follows the same pattern. Multiple branches coexist, overlap, migrate, and occasionally meet, creating a history far richer than earlier generations ever imagined. Around 300,000 years ago, anatomically modern humans begin emerging in Africa. They're only one member of an already diverse human family. Across Western Eurasia, Neanderthals have spent hundreds of thousands of years adapting to colder climates. Their broad chests, powerful limbs, and distinctive facial features reflect countless generations shaped by harsh Ice Age conditions. Far to the east, another mysterious population now known primarily through ancient DNA and a handful of fossils occupies parts of Siberia and Eastern Asia. These people, called Denisovans, after the cave in which the first genetic evidence is discovered, remain among the most enigmatic members of the human family. Fossils attributed to them are remarkably scarce, yet their genetic legacy proves unexpectedly widespread. Nor are these the only human groups inhabiting the ancient world. On the Indonesian island of Flores, a remarkably small body population survives for tens of thousands of years in isolation. Standing little more than 1 meter tall, these humans challenge nearly every assumption about how evolution operates on islands. Their brains are significantly smaller than those of modern humans, yet archaeological evidence suggests they manufacture sophisticated stone tools and successfully hunt local animals. Scholars continue debating the precise origins of this population, but few doubt that they represent another remarkable branch of humanity. Elsewhere, evidence points toward even more diversity. Fossils from the Philippines reveal another diminutive human population adapted to island life. Ancient remains recovered from China display combinations of features that fit imperfectly within existing categories. Some may belong to Denisovans, others may represent populations that have yet to be fully understood. The evidence remains incomplete, and every newly excavated site has the potential to reshape current interpretations. Rather than reducing uncertainty, each discovery often reveals just how much remains unknown. The world these human groups inhabit is astonishingly dynamic. Massive ice sheets periodically spread across northern Europe and North America before retreating again over thousands of years. Sea levels rise and fall by more than 100 meters, exposing enormous land bridges that later disappear beneath the ocean. Britain is sometimes connected directly to continental Europe. Australia, New Guinea and Tasmania become part of a much larger landmass known today as Sahul. Siberia and Alaska are linked through Beringia, a vast plain supporting grasslands, herds of grazing animals, and eventually human travellers moving between continents. Such dramatic environmental changes transform migration routes again and again. Rivers alter their courses, forests advance during warmer periods before yielding to open tundra when temperatures fall. Coastlines shift so dramatically that many of the places where ancient humans once lived now lie beneath the sea, inaccessible to archaeologists, except through specialized underwater exploration. Entire chapters of early human history may remain submerged, forever hidden beneath sediments accumulated since the end of the last ice age. Despite these changing landscapes, one characteristic unites nearly every human population. None live in isolation from nature. Their survival depends upon understanding animal migrations, seasonal plant growth, freshwater sources, weather patterns, and the behavior of predators. Knowledge becomes as valuable as physical strength. Every generation inherits detailed observations about local environments, passing practical wisdom through demonstration rather than written language. A mistake during winter or a failed hunt carries consequences that modern societies rarely experience. Contrary to older stereotypes, prehistoric humans are neither aimless wanderers nor primitive creatures stumbling blindly across the landscape. Archaeological evidence increasingly reveals deliberate planning. Stone suitable for toolmaking is transported across considerable distances. Campsites are positioned to maximize access to water shelter and hunting opportunities. Fire is carefully maintained and used not only for warmth, but also for cooking protection, and perhaps even landscape management. These behaviors appear repeatedly among different human populations, suggesting that intelligence and adaptability are shared traits rather than exclusive achievements of Homo sapiens. Yet important differences also emerge. Neanderthal technology follows one trajectory. Early modern humans introduce innovations that spread with remarkable speed. Island populations develop solutions unique to their isolated environments. Some groups exploit marine resources extensively, while others specialize in large mammals roaming open grasslands. Evolution does not produce identical copies of humanity adapted to every region. Instead, it generates diverse populations, each responding to local pressures through slightly different biological and cultural strategies. Occasionally, these worlds overlap. A valley that supports Neanderthal hunters for generations may later welcome incoming Homo sapiens. Mountain passes become corridors through which different populations unknowingly approach one another. River systems connecting distant regions increase the likelihood of encounters. Sometimes those meetings are probably brief, involving little more than distant observation. At other times, they appear to become far more significant. Ancient DNA demonstrates that at least some of these encounters result in children who carry ancestry from multiple human groups. The family tree is therefore not composed of isolated branches separated forever. At certain moments those branches touch. Exactly how often such interactions occur remains one of paleoanthropology's greatest questions. The archaeological record cannot easily distinguish peaceful exchanges from competition or conflict. Stone tools alone rarely reveal the emotions or intentions of those who made them. What survives in the record suggests a complicated picture. Some regions show evidence of technological similarities spreading between populations. Others indicate long periods during which different groups occupy neighbouring territories without leaving obvious signs of close contact. Human behaviour, even in deep prehistory, refuses to conform to simple narratives. Perhaps the most remarkable realization is how ordinary these vanished people would appear from a distance. A hunting party crossing a snowy plain, smoke rising from a cave entrance at dusk. Children gathering edible plants beside a river. Families sheltering beneath rock overhangs during seasonal storms. Such scenes unfold across countless generations. They laugh, mourn, teach, cooperate and adapt within worlds that feel immediate to them, even though those worlds will eventually vanish beneath changing climates and the passage of time. They do not know they belong to branches destined to disappear. They simply live generation after generation within landscapes that seem as permanent as the mountains surrounding them. Only much later does history reveal the astonishing outcome. Of all these human populations sharing the earth, only one survives into the present day. Every other branch fades from the living world, leaving behind scattered bones, worn stone tools, fragments of DNA, and unanswered questions buried beneath layers of ancient soil. The remarkable age of many humanities slowly gives way to the lonely age of one. As the human family spreads across Africa, Europe, and Asia, the landscape surrounding each population shape lives just as profoundly as biology does. No branch of humanity exists apart from its environment. Mountains dictate migration routes. Rivers determine where camps can survive through dry seasons. Forests conceal prey, while open grasslands reward endurance and cooperation. Over thousands of generations, climate becomes an invisible force, quietly directing the course of evolution with every advancing glacier, every prolonged drought, and every gradual shift in vegetation. The lost branch of humanity does not inherit a stable world. Instead, it occupies one of the most climatically unpredictable periods of the past million years. The Ice Age is not simply a single frozen episode, but a long sequence of colder and warmer intervals. Great continental ice sheets expand across northern latitudes before retreating again. During colder phases, enormous volumes of water become locked inside glaciers, lowering sea levels and exposing land that is now hidden beneath the oceans. During warmer periods, forests reclaim territory, coastlines move inland, and familiar migration routes disappear beneath rising seas. For every human population, these transformations create opportunities as well as dangers. When grasslands spread across Eurasia, enormous herds of mammoth, steppe, bison, wild horses, reindeer, and woolly rhinoceroses flourish. Hunting communities follow these animals across open plains stretching hundreds of kilometers. Yet when climates warm, many of these vast grasslands gradually fragment into forests. Animals shift their ranges, forcing hunters to adapt or relocate. Entire generations grow up watching familiar landscapes slowly transform into something their grandparents would scarcely recognize. The changing environment influences the human body itself. In colder northern regions, stockier physiques conserve heat more efficiently. Broader chests allow greater lung capacity during physically demanding lives in frigid conditions. Powerful muscles become valuable when hunting massive Ice Age mammals or traveling across snow-covered terrain. These characteristics emerge gradually through natural selection. Rather than sudden transformation, reflecting countless generations responding to environmental pressures rather than conscious adaptation. At the same time, human intelligence allows biological evolution to work alongside cultural innovation. Fire becomes more than a source of warmth. It transforms frozen caves into habitable shelters, extends waking hours during long winter nights, hardens wooden tools, cooks difficult foods into digestible meals, and provides protection from predators. Clothing made from animal hides insulates bodies that otherwise could not survive severe winters. Although hides, leather, and woven fibers rarely survive in archaeological deposits, specialized stone tools designed for scraping skins strongly suggest that prehistoric people master these essential technologies long before written history begins. Caves become especially important in many regions, not because ancient humans live exclusively within them, but because caves preserve evidence exceptionally well. Open-air camps are exposed to wind-rain rivers, animals, and countless natural processes that gradually erase signs of occupation. Deep caves, by contrast, often protect bones, tools, charcoal pollen, and even ancient footprints beneath layers of sediment, accumulating over tens of thousands of years. Ironically, modern understanding of prehistoric life is shaped partly by this archaeological accident. People undoubtedly spend much of their lives outside caves, yet caves become the places where their stories survive. Within these protected shelters, traces of everyday existence slowly accumulate. Stone flakes scatter across ancient floors where tools are manufactured and repaired. Hearths leave behind charcoal that can be dated with remarkable precision. Animal bones preserve cut marks showing careful butchering techniques. Tiny fragments of burned seeds reveal seasonal gathering practices. Even microscopic grains of pollen trapped within sediments help reconstruct surrounding vegetation, allowing scientists to visualize landscapes that disappeared tens of thousands of years ago. One surprising discovery emerging from recent decades is just how flexible these ancient populations proved to be. Rather than relying upon a single hunting strategy, they exploit whatever resources local environments provide. Along coastlines, shellfish, fish seals, and seabirds supplement diets. Inland communities pursue deer horses, wild cattle, and smaller mammals. During lean seasons, edible roots, nuts, berries, mushrooms, and insects become valuable sources of nutrition. Survival depends not upon one remarkable invention, but upon the ability to continually adjust as circumstances change. Scholars still debate exactly how large these prehistoric populations are. The evidence remains incomplete because mobile hunter-gatherers leave relatively light archaeological footprints. Nevertheless, most estimates suggest remarkably low population densities compared with later agricultural societies. Entire regions may contain only a few thousand people spread across enormous territories. Communities probably consist of extended families linked through wider social networks, meeting periodically to exchange information, find marriage partners, and strengthen alliances before dispersing once again across seasonal landscapes. Such small populations create unique challenges. A successful hunting season can allow communities to thrive for years, while repeated failures may force difficult decisions about migration or resource sharing. Isolation increases the risk of losing valuable knowledge if experienced elders die unexpectedly. Genetic diversity may also decline when groups remain separated for long periods. These pressures affect every branch of humanity regardless of intelligence or technological skill. Sometimes survival depends simply upon chance encounters with neighboring communities. The rhythms of daily life are shaped by observation rather than clocks or calendars. People learn to recognize subtle changes in animal behavior signaling approaching weather. The flowering of certain plants marks seasonal transitions. The arrival of migratory birds indicates opportunities for hunting or fishing. Children grow into adulthood surrounded by practical ecological knowledge accumulated over generations. This understanding cannot be written down, yet it becomes one of humanity's greatest evolutionary advantages. Perhaps the most extraordinary aspect of these vanished populations is that they inhabit landscapes teeming with formidable competitors. Cave lions, saber-toothed cats in earlier periods, wolves, hyenas, giant bears, and other predators share many of the same environments. Humans are neither the strongest nor the fastest creatures within these ecosystems. Their advantage lies elsewhere in cooperation, planning, communication, and the gradual accumulation of shared experience. Every successful hunt reflects not merely physical ability, but careful coordination among individuals who understand one another's roles. What survives in the archaeological record increasingly suggests that these ancient communities possess sophisticated environmental awareness. Certain stone raw materials are transported across distances exceeding 100 kilometers, implying either extensive seasonal movement or exchange between neighboring groups. Camps repeatedly appear near strategic river crossings, where migrating animals predictably gather. Specialized hunting locations differ from longer-term residential sites. Such patterns reveal deliberate organization rather than random wandering. Even so, nature always retains the upper hand. A sequence of unusually harsh winters can reduce herbivore populations. Prolonged drought shrink rivers into isolated pools. Volcanic eruptions darken skies and disrupt ecosystems hundreds or even thousands of kilometers away. Slowly advancing glaciers compress suitable habitats into smaller refuges, where multiple human populations may suddenly find themselves competing for diminishing resources. The environment that once sustains them can over centuries become increasingly unforgiving without any single dramatic catastrophe. The lost branch of humanity therefore develops within a world defined by constant adjustment. Every generation inherits not certainty but change. Success belongs less to those who dominate nature than to those who respond most effectively when nature transforms itself once again. This relentless partnership between human adaptability and environmental instability will eventually shape one of the greatest mysteries in our evolutionary history, determining which branches endure and which quietly disappear into the deep silence of time. The image of prehistoric humans as little more than desperate survivors has slowly faded with every new excavation. The accumulated evidence now paints a far richer picture, revealing lives filled not only with struggle, but also with planning, learning, cooperation, and remarkable ingenuity. The lost branch of humanity does not simply endure the ancient world, it actively shapes its place within it, developing behaviors that blur many of the distinctions once believed to separate modern humans from their extinct relatives. A single stone tool can appear deceptively simple when displayed inside a museum case. Its sharp edges, carefully struck from a prepared core, seem crude beside polished metal or modern machinery. Yet creating that tool requires far more than brute force. The maker must understand the internal structure of stone, anticipate how each blow will travel through the material, and visualize the final shape long before the first strike is delivered. A mistake made early in the process cannot easily be corrected. Every successful tool reflects knowledge accumulated through years of observation and repeated practice. Archaeologists increasingly recognize that this knowledge is rarely invented anew by each individual. Instead, it is taught. Young members of a community likely spend countless hours watching experienced toolmakers before attempting the craft themselves. Broken practice pieces discovered alongside expertly finished implements hint at long apprenticeships extending across childhood and adolescence. Skills are passed from one generation to the next, forming cultural traditions that survive for thousands of years. In some regions, distinctive methods of shaping stone remain remarkably consistent across immense stretches of time, suggesting that communities value established techniques while gradually refining them. The same pattern appears in hunting. Large Ice Age animals are formidable opponents. An adult mammoth outweighs even the largest human group by many times. Woolly rhinoceroses possess tremendous strength and dangerous horns. Even smaller prey such as wild horses or red deer can seriously injure hunters if approached carelessly. Successful hunting therefore depends upon careful planning rather than reckless courage. People study migration routes, recognize seasonal behavior, exploit natural bottlenecks in the landscape, and coordinate movements with extraordinary precision. Evidence from archaeological sites occasionally reveals the scale of these operations. Hundreds of animal bones accumulate at locations where herds repeatedly pass through valleys or become trapped against natural barriers. Stone spear points are recovered alongside butchered remains bearing clear-cut marks. Some sites indicate that hunters process enormous quantities of meat within relatively short periods, preserving portions through drying, smoking or freezing during cold seasons. Such achievements require cooperation among many individuals rather than isolated acts of survival. Food procurement, however, extends well beyond hunting large mammals. The archaeological record increasingly demonstrates a flexible approach to nutrition. Communities gather nuts rich in fat before winter arrives. They harvest edible roots hidden beneath the soil, collect berries during brief growing seasons, and exploit freshwater fish whenever rivers permit. Coastal populations develop impressive knowledge of tidal rhythms, shellfish beds, and marine mammals. This dietary diversity helps buffer communities against environmental uncertainty. If one food source declines, others may still provide enough nourishment to sustain the group. Fire remains central to nearly every aspect of daily life. Beyond warmth and cooking, controlled fire transforms social existence. Evening gatherings around hearths extend productive hours after sunset. Food cooked over flames becomes easier to digest, allowing greater nutritional returns from available resources. Smoke discourages insects and predators. Heated stones may assist in preparing hides or processing plant materials. Some researchers even suggest that firelight encourages longer periods of social interaction, strengthening relationships through storytelling, teaching, and shared experience, although the evidence for the exact nature of these conversations can never be recovered. Shelters vary dramatically according to local conditions. In limestone regions, caves and rock overhangs provide natural protection against weather. Across open plains, people likely construct temporary structures using wooden poles, animal hides, grasses, and mammoth bones where timber is scarce. While these organic materials rarely survive tens of thousands of years, patterns of post holes, concentrations of tools, and carefully arranged hearths allow archaeologists to reconstruct surprisingly sophisticated living spaces. These are not random camps, but organized environments in which different activities occupy distinct areas. Children play an essential role in this ancient world, even though their presence often leaves only subtle traces. Tiny footprints preserved in ancient mud occasionally reveal groups of young individuals accompanying adults through cave passages or across lake shores. Small stone tools displaying signs of imperfect craftsmanship may represent early learning rather than functional equipment. Dental growth patterns preserved within juvenile fossils provide insight into childhood development, health, and nutrition. These fragments remind researchers that prehistoric communities are composed not merely of hunters, but of complete families spanning multiple generations. One of the most striking discoveries concerns the treatment of vulnerable individuals. Several fossil skeletons belonging to Neanderthals and other ancient humans display severe injuries that heal long before death. broken limbs mend successfully. Serious head trauma shows evidence of recovery. Arthritic joints continue functioning for years despite chronic pain. One famous individual survives the loss of an arm and significant visual impairment. Such people could not easily obtain food or defend themselves without assistance. Their survival strongly suggests that companions provide long-term care-sharing resources with those temporarily or permanently unable to contribute fully. This willingness to care for injured members reflects a level of social cohesion that older portrayals of prehistoric life often overlook. Cooperation is not merely advantageous, it becomes essential. Small populations cannot afford to abandon experienced hunters, knowledgeable elders, or skilled toolmakers whenever illness strikes. Every individual represents years of accumulated knowledge about landscapes, animals, weather, and survival techniques. Preserving that knowledge benefits the entire community. Scholars continue debating the extent to which extinct human groups engage in symbolic behavior. Some archaeological sites contain pigments such as red ochre carefully collected and transported despite having little practical value. Eagle talons bearing cut marks may have served as ornaments. Feathers from large birds appear to have been deliberately gathered in certain regions. Perforated animal teeth could have been suspended as personal decorations. None of these discoveries alone proves the existence of complex symbolic culture, yet together they suggest minds capable of attaching meaning beyond immediate survival. The evidence remains incomplete and caution is necessary. Modern observers naturally wish to recognize familiar behaviors within ancient populations. Similar objects may have served entirely different purposes. Nonetheless, each new discovery gradually erodes the once common belief that only Homo sapiens possesses creativity, planning, or emotional depth. Instead, the differences between surviving and vanished branches of humanity appear increasingly subtle. Perhaps nowhere is this more apparent than in the rhythms of ordinary life. Morning begins with tending embers preserved overnight beneath ash. Small groups prepare to gather plants while others inspect hunting equipment worn down by previous expeditions. Children imitate adults, gradually learning countless practical skills through observation rather than formal instruction. Elders contribute memory, experience, and judgment, accumulated across decades of seasonal migrations. Evenings bring shared meals, maintenance of tools, preparation for changing weather, and quiet moments around the fire before darkness settles across the Ice Age landscape. For thousands upon thousands of years, such scenes repeat across continents. Families grow, seasons change, knowledge passes forward, and communities adapt to the ever-changing world surrounding them. Nothing within these daily routines suggests that entire branches of humanity are moving slowly toward extinction. From their own perspective, life simply continues one generation after another, beneath the same stars that still shine over the modern world. The story of the lost branch of humanity changes forever, not because archaeologists suddenly uncover an entire forgotten civilization, but because they learn to recognize extraordinary significance in objects that once seemed almost ordinary. A weathered skull cap, an isolated tooth, a fragment of jaw no larger than the palm of a hand or a finger bone, scarcely longer than a fingernail, gradually become some of the most valuable scientific discoveries ever recovered. Each fossil adds another sentence to a story written across hundreds of thousands of years, and each new sentence forces researchers to revise chapters they once believed were complete. The search begins long before modern technology transforms archaeology. During the 19th century, scattered human remains occasionally emerge from caves, gravel pits, and river terraces throughout Europe. Many are initially misunderstood. Some scholars dismiss them as unusual examples of modern humans. Others argue that disease or injury has distorted otherwise ordinary skeletons. Only after repeated discoveries from widely separated locations does a different possibility begin to take shape. These bones belong to people who are unmistakably human, yet consistently different in ways that cannot easily be explained by individual variation. The realization develops slowly because scientific understanding itself evolves. Early excavators often lack precise methods for recording the position of fossils within archaeological layers. Radiocarbon dating has not yet been invented. DNA analysis remains unimaginable. Even careful researchers must rely largely upon anatomy and geological context. As a result, debates continue for decades over the identity and age of newly discovered remains. Some conclusions later prove remarkably accurate. Others are overturned completely as new evidence accumulates. By the middle of the 20th century, excavation techniques become increasingly systematic. Archaeologists no longer focus only on spectacular skeletons. They carefully record every stone tool fragment of charcoal pollen grain and animal bone surrounding human remains. Each object contributes context. A fossil separated from its environment can reveal only limited information, but one preserved alongside hearths, butchered animals, and distinctive tools becomes part of a much richer narrative. Archaeology gradually shifts from collecting remarkable objects to reconstructing entire ancient lives. Among the most informative evidence are the bones themselves. Human skeletons preserve an astonishing amount of biological information. Teeth record childhood growth through microscopic layers that develop much like tree rings. Bones reveal repeated physical stresses caused by climbing, carrying, hunting, or traveling across rugged terrain. Healed fractures testify to injuries survived years before death. Joint surfaces display arthritis accumulated over decades of demanding movement. Even chemical elements incorporated into skeletal tissue can preserve clues about long-term diet and changing environments. Neanderthal fossils, for example, consistently display bodies adapted to physically demanding lives. Their limb bones are thick and powerfully built. Muscle attachment sites suggest exceptional strength. Rib cages are broader than those of most modern humans, while their pelvises differ in subtle but important ways. Their faces project farther forward, and prominent brow ridges frame deep-set eyes. Yet despite these distinctive characteristics, the overall structure remains recognizably human. Looking into a reconstructed Neanderthal face often produces an unsettling sense of familiarity. The differences are real, but so are the similarities. Children's skeletons provide equally valuable insights. Growth patterns indicate that young Neanderthals develop along trajectories broadly comparable to those of modern humans, although certain aspects of maturation may proceed at slightly different rates. Tiny milk teeth preserve chemical signatures reflecting breastfeeding and early childhood nutrition. Rare infant burials offer heartbreaking glimpses into communities that experience loss just as modern families do. Although archaeology cannot recover emotions directly, careful burial practices in some cases suggest that the deaths of children carry significance extending beyond simple disposal of remains. One particularly revealing source of information comes from microscopic damage preserved on fossil teeth. Fine scratches and pits reflect different types of food consumed throughout life. In colder environments, diets often rely heavily upon meat from large herbivores. Elsewhere, evidence points toward greater consumption of plants, nuts, and other resources. In certain regions, traces of cooked starch become trapped within hardened dental plaque, indicating that plant foods play a more important role than once assumed. Ancient teeth thus preserve records of meals eaten tens of thousands of years before agriculture exists. Scholars also study evidence of disease. Contrary to romantic images of pristine prehistoric health, ancient populations face numerous biological challenges. Dental abscesses, infections, parasites, degenerative joint disease, and traumatic injuries all appear within the fossil record. Some individuals suffer repeated fractures consistent with dangerous hunting activities. Others exhibit developmental abnormalities likely present from birth. The remarkable aspect is not the existence of illness, but the frequency with which serious conditions show signs of long-term survival. Communities repeatedly care for individuals who cannot possibly recover alone. The evidence remains incomplete because fossil preservation is exceptionally rare. Most humans who ever live leave no recoverable skeleton. Countless generations disappear without trace as bones dissolve in acidic soils or are scattered by animals and erosion. Every fossil discovered today represents an extraordinary combination of circumstances. The individual must die under conditions favorable for preservation, remain undisturbed for tens of thousands of years, survive geological processes that destroy surrounding deposits, and finally be uncovered by researchers before natural weathering erases the remaining evidence. The rarity of such events explains why each new discovery has the potential to transform scientific understanding. One of the most dramatic examples occurs in a remote Siberian cave where archaeologists recover what appears to be an insignificant finger bone from a young girl. At the time of excavation, nothing about the fragment suggests global importance. Its size is modest. Its appearance is unremarkable, yet advances in molecular biology soon reveal that this tiny fossil belongs neither to modern humans nor to Neanderthals. Instead, it represents an entirely distinct human population previously unknown to science. The discovery of the Denisovans demonstrates that an entire branch of humanity can remain invisible until a single fragment of bone unlocks its hidden identity. Other fossils continue to blur traditional boundaries. A jaw recovered from the Tibetan plateau displays characteristics later linked to Denisovans, suggesting these ancient people inhabit high-altitude environments once thought impossible for prehistoric humans. In another extraordinary discovery, researchers identify the remains of a young girl whose mother is Neanderthal and whose father is Denisovan. This single skeleton provides direct evidence that different branches of humanity not only encounter one another but also produce children together. The family tree proves even more interconnected than scientists had imagined. What survives in the record suggests that human evolution is not a sequence of isolated species replacing one another in orderly progression. Instead, populations expand, contract separate, reunite, and occasionally merge. Fossils reveal anatomical differences, but they also expose countless connections. Every newly excavated cave, river terrace, or mountain shelter carries the possibility of another unexpected discovery, capable of rewriting familiar narratives. The lost branch of humanity therefore emerges not through one spectacular revelation, but through thousands of careful observations accumulated across generations of scientific work. Every bone measured, every tooth examined under magnification, every layer of sediment recorded with painstaking precision contributes another fragment of a story that remains unfinished. The deeper researchers look into ancient bones, the more vividly the vanished people who once carried them begin to step out of the darkness of prehistory and into the growing light of modern understanding. For more than a century, fossils remain the primary witnesses to humanity's distant past. Bones reveal anatomy, stone tools hint at behavior, and ancient campsites preserve fragments of everyday life. Yet there are limits to what even the most carefully excavated skeleton can reveal. A skull cannot explain family relationships separated by thousands of kilometers. A spear point cannot identify distant ancestors. Two populations may appear physically similar while having followed very different evolutionary paths. Conversely, groups with noticeably different appearances may prove surprisingly closely related. The answers lie hidden inside something far smaller than any fossil can display: the microscopic sequences of DNA preserved within ancient cells. The possibility of recovering genetic material from prehistoric humans once seems almost impossible. DNA is an extraordinarily fragile molecule. After death, cells begin to break apart. Water, oxygen, bacteria, fungi, changing temperatures, and countless chemical reactions slowly destroy genetic material. Under ordinary conditions, very little survives beyond a few thousand years. Researchers therefore assume that the genomes of Ice Age humans are permanently lost, erased by time long before modern science has the ability to read them. A few exceptional environments, however, preserve the impossible. Deep caves remain cool throughout the year. Permanently frozen ground slows biological decay. Dry sediments protect delicate tissues from moisture. Within these rare settings, tiny fragments of ancient DNA survive inside dense bones and teeth, waiting silently for tens of thousands of years. Recovering them is only the beginning. Scientists must separate authentic ancient molecules from modern contamination introduced by excavators, laboratory workers, or even microscopic organisms living within the surrounding soil. The technical challenge is immense. Researchers wear protective clothing, masks, gloves, and specialized equipment while working inside laboratories designed specifically for ancient DNA. Air filtration systems reduce contamination. Every sample is carefully cleaned before a tiny portion is removed for analysis. Even then, the overwhelming majority of recovered genetic material often belongs not to humans, but to bacteria and fungi that colonize the remains after burial. Finding authentic prehistoric DNA resembles searching for a handful of meaningful words scattered throughout an enormous library of unrelated text. Despite these obstacles, remarkable breakthroughs begin appearing during the closing years of the 20th century and accelerate dramatically in the decades that follow. Complete genomes are reconstructed from Neanderthal remains preserved in European and Asian caves. Suddenly, researchers possess something far more informative than skeletal measurements. They can compare entire genetic sequences with those of living people around the world. The results overturn long-standing assumptions almost immediately. For many years, one popular hypothesis suggests that modern humans leaving Africa completely replace every earlier human population they encounter, leaving no biological descendants outside their own lineage. Fossils alone cannot fully resolve this debate. Ancient DNA changes everything. Comparisons reveal that people living today outside Africa inherit approximately 1 to 2% of their DNA from Neanderthals. The exact percentage varies among populations, but the conclusion remains unmistakable. At some point after modern humans expand into Eurasia, they meet Neanderthals, and those encounters include successful reproduction. This discovery fundamentally reshapes the story of human evolution. Extinction no longer appears as a clean ending in which one population simply replaces another. Instead, disappearing groups leave fragments of themselves behind within the genomes of future generations. Their physical populations eventually vanish, yet portions of their biological legacy continue traveling through time, inside millions and eventually billions of descendants who may never know those ancient ancestors existed. The surprises do not end there. Analysis of the tiny finger bone recovered from Denisova Cave reveals a genome unlike anything previously identified. This individual belongs neither to Homo sapiens nor to Neanderthals, but to another branch that diverges from the Neanderthal lineage hundreds of thousands of years earlier. Even more astonishing, modern populations in parts of Oceania, New Guinea, Australia, and several regions of Southeast Asia carry measurable amounts of Denisovan ancestry. In some communities, Denisovan DNA reaches several % of the genome, indicating repeated interactions between these mysterious people and the ancestors of present-day populations. The geographic implications are extraordinary. Fossils of Denisovans remain exceptionally rare, yet their genetic influence stretches across enormous distances. This contrast suggests that the archaeological record captures only a tiny fraction of their true distribution. Entire populations may once occupy landscapes where environmental conditions fail to preserve bones. The evidence remains incomplete, but genetics reveals their former presence, even where fossils have yet to be discovered. One of the most fascinating inherited traits linked to Denisovan ancestry involves life at high altitude. Populations living on the Tibetan Plateau possess genetic variants that help regulate oxygen use under thin atmospheric conditions. Studies indicate that one of these beneficial variants likely enters the modern human gene pool through ancient Denisovan ancestors. What begins as an encounter tens of thousands of years ago continues influencing human physiology today, allowing millions of people to thrive in environments where oxygen levels are dramatically lower than at sea level. Neanderthal genes also continue shaping modern biology in subtle ways. Certain inherited variants affect aspects of the immune system, helping early modern humans confront unfamiliar pathogens encountered after leaving Africa. Others influence skin characteristics, hair biology, or responses to sunlight in northern environments. Some inherited sequences appear beneficial under ancient conditions, but may contribute to increased susceptibility to particular illnesses in modern societies. Evolution rarely produces perfect solutions. Traits advantageous in one environment can become less useful or even harmful after circumstances change. Scholars still debate exactly how often interbreeding occurs and under what social circumstances these encounters take place. Ancient genomes suggest that such events are relatively uncommon compared with reproduction within each population, yet they occur often enough to leave lasting genetic signatures. Whether these meetings involve peaceful coexistence, temporary alliances, isolated family relationships, or more complicated circumstances remains impossible to determine from DNA alone. Genes preserve biological connections but remain silent regarding the emotions, intentions, or experiences of the individuals involved. Another astonishing discovery emerges when scientists sequence the DNA of a teenage girl from Denisova Cave. Her genome reveals that her mother is Neanderthal, while her father is Denisovan. Rather than representing distant episodes separated by millennia, interaction between different human groups clearly happens within individual lifetimes. This young girl becomes direct evidence that branches of humanity not only encounter one another, but also form families across evolutionary boundaries. The growing field of ancient genomics continues producing unexpected revelations. Researchers now recover fragments of human DNA directly from cave sediments, even when no visible bones remain. Soil itself becomes an archive, preserving microscopic traces shed through skin cells, bodily fluids, and decaying tissue. Entire occupations of ancient caves can sometimes be detected genetically, despite the absence of identifiable skeletons. This remarkable technique expands the search for vanished populations far beyond traditional fossil discoveries. Every new genome reinforces a profound realization. Human evolution is not a story of isolated species marching independently towards separate destinies. It is a web of migrations, separations, reunions, adaptations, and occasional exchanges that unfold over hundreds of thousands of years. The lost branch of humanity has not disappeared completely. Fragments of its biological inheritance continue circulating through living populations across the globe, quietly reminding us that extinction can leave echoes far more enduring than anyone once imagined. The first meeting between two different branches of humanity leaves no written account, no carved monument, and no preserved memory that can describe what either side sees. There are no witnesses capable of recording the expressions on unfamiliar faces or the hesitation that may accompany those first moments. Yet somewhere in the vast landscapes of Ice Age Eurasia, such encounters undoubtedly take place. Small bands of modern humans moving gradually out of Africa enter territories that have been occupied by other human populations for hundreds of thousands of years. They do not step into an empty continent. They step into someone else's homeland. The scale of these migrations unfolds over thousands of years rather than a single dramatic journey. Early Homo sapiens expand through the Middle East before spreading into Europe, Central Asia, Eastern Asia, and eventually beyond. Their movements are neither continuous nor unstoppable. Climate shifts repeatedly open and close migration corridors. Some pioneering groups disappear without leaving lasting descendants. Others settle successfully adapting to unfamiliar environments generation after generation. Progress is measured not in months but in centuries. Across much of Western Eurasia, Neanderthals remain deeply established. Their ancestors have occupied these regions through repeated Ice Age cycles, learning the rhythms of local ecosystems over immense spans of time. They know the migration routes of reindeer and bison. They understand where fresh water remains available during dry seasons and which caves provide reliable shelter during severe winters. Every valley, river crossing and mountain pass holds generations of accumulated knowledge. Incoming modern humans may bring different technologies and social traditions, but they enter landscapes already thoroughly understood by those who came before. Exactly how the first encounters unfold remains one of the greatest unanswered questions in prehistoric archaeology. Fossils and stone tools preserve actions but rarely intentions. A campsite abandoned thousands of years ago cannot reveal whether neighbouring groups exchange gifts, avoid one another, or compete over hunting grounds. The archaeological record offers only scattered clues, leaving scholars to construct cautious interpretations rather than definitive narratives. Some evidence hints at long periods during which different populations occupy nearby regions without immediate replacement. In parts of Europe, archaeological layers associated with Neanderthals and those linked to early modern humans overlap within relatively short chronological intervals. This pattern suggests that both populations exist within the same broader landscapes for thousands of years. Such coexistence creates numerous opportunities for contact, whether direct or indirect. Not every meeting necessarily involves face-to-face interaction. Communities may recognize the presence of others through abandoned campsites, footprints preserved in mud smoke rising from distant valleys, or animal carcasses bearing unfamiliar butchering techniques. Hunters following migrating herds could discover freshly worked stone tools, unlike those produced by their own traditions. Such silent evidence alone would indicate that another human population shares the landscape. Stone technology occasionally provides subtle hints of cultural influence. Certain tool-making methods appear to spread across neighbouring regions, in ways suggesting that ideas rather than people alone move between communities. Scholars continue debating whether these similarities result from direct contact-independent innovation or observation from a distance. The evidence remains incomplete, and no single explanation fully accounts for every archaeological pattern. Human societies are capable of learning through many different pathways. Ancient DNA, however, provides one conclusion beyond reasonable doubt. At least some encounters lead to children. Interbreeding between Homo sapiens and Neanderthals occurs multiple times across different regions. Similar exchanges take place between modern humans and Denisovans in Eastern Asia and beyond. These events are sufficiently frequent to leave lasting genetic signatures, yet uncommon enough that each population largely maintains its own distinctive identity for thousands of years. The existence of children with mixed ancestry raises profound questions about everyday life in these ancient worlds. Successful reproduction implies far more than a brief encounter. It suggests biological compatibility, at least occasional social acceptance, and opportunities for individuals from different populations to remain together long enough to form families. Exactly how these relationships are viewed by surrounding communities can never be known, but the genomes preserved today testify that they do indeed occur. The remarkable Denisovan Neanderthal teenager discovered through genetic analysis offers perhaps the clearest illustration of this interconnected past. Her mother belongs entirely to one population, while her father belongs primarily to another. This is not evidence of distant ancestry diluted over countless generations. It is evidence of immediate family ties. Somewhere in the deep past, two individuals from different branches of humanity share a life long enough to bring a child into the world. Their daughter grows into adolescence before dying, leaving behind the small fragment of bone that eventually reveals her extraordinary story tens of thousands of years later. Competition undoubtedly exists as well. Human populations relying upon similar prey naturally encounter overlapping resource needs. During periods of climatic deterioration, shrinking habitats force communities into increasingly confined regions where food becomes less predictable. Larger social networks, more efficient technologies, or greater demographic resilience may provide advantages under such conditions. Yet competition need not always involve open conflict. Simply occupying favorable territories, exploiting resources more effectively, or maintaining higher birth rates can gradually shift the balance over many generations. Some researchers argue that modern humans possess broader exchange networks linking distant communities together. Stone materials transported over remarkable distances, ornaments shared across large regions, and increasingly standardized technologies may indicate stronger long-range connections. If so, these wider networks could prove valuable during environmental crises. Communities experiencing local shortages might receive information marriage partners or resources from neighboring groups, increasing resilience against temporary hardship. Neanderthals, however, should not be viewed as isolated or incapable. Evidence increasingly reveals that they also travel significant distances, exploit diverse environments, and adapt repeatedly to changing climates. They survive in Eurasia for more than 400,000 years, an achievement requiring extraordinary resilience. Any explanation for their eventual disappearance must account for this remarkable longevity. A population capable of enduring repeated ice age cycles cannot reasonably be dismissed as evolutionarily unsuccessful. What survives in the archaeological record also suggests moments of remarkable convergence. Both Neanderthals and Homo sapiens manufacture carefully shaped stone tools, control fire, hunt large animals, care for injured companions, and perhaps employ pigments or ornaments under certain circumstances. The differences between them become increasingly nuanced as evidence accumulates. Earlier portrayals emphasizing sharp divisions give way to recognition of substantial overlap in behavior and capability. Nevertheless, subtle distinctions can carry significant long-term consequences. Slightly larger social networks, marginal improvements in information sharing, incremental technological innovations, or modest demographic advantages may accumulate over thousands of years. Evolution often favors not dramatic superiority but persistent adaptability. A population that consistently recovers more quickly after environmental setbacks gradually expands while another slowly contracts. No single generation witnesses the full process. Only archaeology looking backward across immense spans of time can perceive the gradual shift. Perhaps the most moving aspect of these encounters is their ordinariness. Individuals meeting along rivers, exchanging cautious glances across open valleys, sharing knowledge of migration routes or raising children of mixed ancestry, do not know they are participating in one of the defining chapters of human history. They cannot foresee that nearly every branch of their extended family tree will eventually disappear, leaving only one lineage to inherit the earth. They simply navigate the challenges of daily existence within landscapes where multiple kinds of humans briefly share the same horizon before time slowly narrows that extraordinary diversity to a single surviving branch. For hundreds of thousands of years, the many branches of humanity endure conditions that would seem almost unimaginably unstable by modern standards. Entire ecosystems expand and contract with astonishing regularity. Rivers carve new channels through ancient valleys before drying into scattered pools. Forests spread across continents only to retreat once more before advancing ice. Animals that dominate one age vanish from the next, replaced by species better suited to changing conditions. The Earth itself is constantly rewriting the rules of survival, and every human population must adapt or slowly disappear. The Ice Age is often imagined as a world locked beneath endless snow, but the reality is far more complex. It consists of repeated climatic oscillations extending over hundreds of thousands of years. During colder phases, immense glaciers stretch across northern Europe, reaching farther south than most people today can easily imagine. Vast quantities of water become trapped inside these frozen masses, lowering global sea levels and exposing enormous coastal plains. During warmer intervals, the glaciers retreat, sea levels rise, forests reclaim abandoned ground, and familiar migration routes vanish beneath expanding oceans. To prehistoric humans, these transformations do not occur overnight. Most unfold over many generations, making them difficult to recognize within a single lifetime. A child grows into old age while noticing only subtle shifts in vegetation or seasonal weather. Yet when compared across centuries, the changes become profound. Valleys once covered by grasslands gradually fill with dense woodland. Herds that traditionally migrate through a region alter their routes. Rivers supporting countless generations begin flowing differently or disappear altogether. For small populations, these slow environmental changes create enormous challenges. Every hunting strategy depends upon understanding the predictable movements of prey. If those patterns change, knowledge accumulated over generations becomes less reliable. Communities must learn unfamiliar landscapes while competing for increasingly uncertain resources. Success depends not simply upon intelligence, but upon the speed with which cultural knowledge can adapt to changing ecological realities. One particularly difficult period arrives roughly between 70,000 and 50,000 years ago, although regional conditions vary considerably. Climate fluctuations become especially rapid in parts of Eurasia. Temperatures swing dramatically over relatively short geological intervals. Forest boundaries advance and retreat. Open steppe environments fragment into isolated patches. Large herbivores shift their distributions in response, carrying with them the predators and human hunters who rely upon their movements. The archaeological record preserves signs of repeated relocation. Caves occupied for thousands of years are abandoned as local conditions deteriorate. New camps appear hundreds of kilometers away. Stone materials sourced from distant outcrops indicate increasingly extensive movement across landscapes. These migrations are rarely straightforward journeys toward better conditions. Instead, they involve continual adjustment, as favorable habitats expand, shrink, or disappear altogether. Competition intensifies wherever suitable environments become concentrated. Refugia regions, where climate remains relatively stable during harsh periods, acquire growing importance. Southern Europe, parts of the Middle East, and several areas of Central and East Asia serve as biological sanctuaries, supporting plants, animals, and human communities when surrounding territories become less hospitable. Such regions naturally attract multiple populations seeking reliable food and shelter. Scholars still debate the precise role climate plays in the disappearance of Neanderthals and other ancient human groups. Earlier explanations often portray environmental deterioration as the single decisive cause. Modern research paints a more nuanced picture. Neanderthals survived numerous severe climatic episodes over hundreds of thousands of years. They repeatedly demonstrate extraordinary resilience, adapting successfully to conditions that would overwhelm many later societies. Clearly, climate alone cannot fully explain their eventual extinction. Instead, environmental instability may act as a force that magnifies existing pressures. A population already limited in number becomes more vulnerable when habitats shrink. Reduced access to prey lowers birth rates and increases mortality. Smaller communities become increasingly isolated from one another, reducing opportunities for exchanging marriage partners and maintaining genetic diversity. Once demographic decline begins, recovery becomes progressively more difficult. The environment does not necessarily eliminate populations directly. Rather, it creates conditions under which other challenges become increasingly difficult to overcome. Volcanic eruptions occasionally add further uncertainty. One of the largest eruptions of the late Pleistocene occurs at Lake Toba on the Indonesian island of Sumatra, approximately 74,000 years ago. Ash spreads across enormous areas of Asia. Earlier theories suggest this eruption nearly drives humanity to extinction through a prolonged volcanic winter. More recent evidence presents a more cautious interpretation. Although the eruption is undoubtedly immense, its effects appear uneven across different regions, and no single explanation fully accounts for observed archaeological patterns. Nevertheless, such catastrophic events illustrate the unpredictable forces capable of reshaping ancient ecosystems. Seasonality also exerts constant pressure. Winters across Ice Age Eurasia are long and unforgiving. Food availability declines sharply. Hunting success becomes less predictable as snow ice and severe weather complicate travel. Communities must preserve sufficient resources during favorable months to survive periods of scarcity. Failure in one season may not prove fatal immediately, but repeated shortages gradually weaken entire populations. Large predators remain formidable competitors throughout these changing landscapes. Cave lions, wolves, hyenas, and bears pursue many of the same herbivores hunted by humans. During periods when prey populations decline, competition between predators naturally intensifies. Human communities must not only locate food but also defend carcasses, protect vulnerable members, and secure safe shelter against increasingly desperate animals. Water presents another recurring challenge. Glacial environments often appear frozen, yet access to liquid fresh water remains surprisingly limited during certain seasons. Rivers may freeze solid or become dangerous to cross. Melting snow provides temporary relief but can also create flooding and unstable terrain. Communities possessing intimate knowledge of springs, sheltered valleys, and dependable water sources gain important advantages over newcomers unfamiliar with local geography. Despite these hardships, ancient humans repeatedly demonstrate extraordinary adaptability. Archaeological evidence shows continued innovation in hunting strategies, shelter, construction, clothing production, and resource exploitation. Rather than responding passively to environmental change, they constantly experiment with new solutions. Flexible diets broaden nutritional options. Improved clothing expands habitable territory. Cooperative social networks reduce individual risk during periods of scarcity. These adaptations help many populations survive conditions that fluctuate dramatically over thousands of years, yet resilience has limits. Every environmental crisis consumes energy, reduces resources, and places additional strain upon already small communities. Recovery after one difficult period may be possible. Recovering after repeated setbacks across many generations becomes increasingly uncertain. Climate does not act as an executioner delivering a sudden blow. It behaves more like a patient sculptor, gradually reshaping landscapes, opportunities, and probabilities until some branches of humanity find themselves living ever closer to the edge of survival. From the perspective of individuals living through these changes, the world still feels familiar. Children are born, families travel established routes, hunters follow migrating animals, and fires burn each evening beneath protective rock shelters. No one senses that the slow accumulation of environmental pressures is steadily narrowing the possibilities available to future generations. The transformation is almost invisible while it unfolds. Only tens of thousands of years later, when archaeologists compare ancient camps separated by immense spans of time, does the full pattern emerge. The changing planet has quietly become one of the most powerful forces shaping which branches of humanity endure and which gradually fade into silence. By the time the last Neanderthal communities occupy the western edges of Eurasia, and the mysterious Denisovan populations become increasingly difficult to trace, in the archaeological record something irreversible is already underway. The diversity that defines humanity for hundreds of thousands of years begins to contract. One branch after another fades from the landscape until only a single surviving lineage remains. Yet the process is neither sudden nor simple. No abandoned battlefield marks the end. No dramatic natural disaster sweeps every vanished population away at once. Instead, extinction unfolds as a slow accumulation of pressures that eventually become impossible to escape. For decades, scientists search for one decisive answer. Was it climate? Was it competition with Homo sapiens? Did unfamiliar diseases spread through isolated populations? Were the last surviving communities simply too small to recover from ordinary losses? Each explanation appears convincing when considered alone, yet each also encounters important difficulties. The deeper researchers investigate, the more apparent it becomes that no single cause fully explains the disappearance of humanity's lost branches. Climate remains one of the strongest candidates, but not because it suddenly becomes hostile. Neanderthals have already survived repeated glacial advances and warmer interglacial periods long before modern humans arrive in Europe. They demonstrate remarkable resilience over more than 400,000 years. Any explanation relying solely upon environmental change must account for this extraordinary endurance. If climate alone cannot eliminate them during earlier ice age cycles, why should it suddenly do so later? Many researchers now argue that the answer lies in timing rather than severity. Toward the final stages of Neanderthal existence, environmental instability coincides with several additional pressures that together prove increasingly difficult to overcome. Habitats become fragmented. Suitable hunting territories shrink into isolated pockets. Animal populations fluctuate unpredictably. At precisely the same time, expanding Homo sapiens populations enter many of these regions. Each individual challenge might be survivable on its own. Combined, they begin reinforcing one another. Population size emerges as another critical factor. Modern genetic studies indicate that Neanderthal communities may have remained surprisingly small for long periods. Rather than occupying Europe in dense numbers, they likely exist as scattered groups separated by considerable distances. Individual bands may contain only a few dozen members, while neighbouring communities remain days or even weeks apart. Such low population density creates hidden vulnerabilities. Small populations are inherently fragile. A harsh winter, a failed hunting season, or an outbreak of disease may eliminate enough individuals to disrupt the balance between generations. The death of several experienced hunters affects food security. The loss of elders removes irreplaceable environmental knowledge accumulated over decades. Fewer potential marriage partners reduce genetic diversity. Recovery becomes increasingly difficult because every individual carries proportionally greater importance within the community. Genetic evidence supports this concern. Some Neanderthal genomes display signs of prolonged isolation and limited genetic variation. Close relatives occasionally reproduce because alternative partners are simply unavailable. This does not imply that every Neanderthal community experiences severe inbreeding, but it does suggest that certain populations become increasingly isolated as suitable habitats contract. Reduced genetic diversity may limit resilience when confronting new diseases or changing environmental conditions. Disease itself remains an intriguing but difficult hypothesis. As modern humans expand into Eurasia, they carry pathogens shaped by their own evolutionary history. Neanderthals may possess little resistance to certain infections, just as populations throughout later human history often suffered devastating consequences after contact with unfamiliar diseases. However, direct evidence for epidemic outbreaks during the late Pleistocene remains extremely limited. Ancient pathogens rarely preserve well enough for confident identification. Scholars therefore treat disease as a possible contributing factor rather than a proven primary cause. Competition for resources likely plays a more subtle role than earlier theories suggest. The archaeological record does not reveal widespread evidence of prolonged warfare between Homo sapiens and Neanderthals. Violent encounters undoubtedly occur at times, as conflict is hardly unique to modern societies, but there is little indication of systematic extermination. Instead, competition probably resembles countless small advantages, accumulating gradually over many generations. Modern humans may maintain somewhat larger social networks extending across greater distances. These broader connections facilitate the exchange of stone materials, innovative technologies, and valuable information regarding changing environments. During periods of local scarcity, communities linked through extensive relationships may relocate more easily or receive assistance from neighboring groups. Such advantages need not be dramatic. Even modest improvements in communication and cooperation can significantly enhance long-term survival when environmental conditions deteriorate. Technological flexibility may also contribute. Around 50,000 years ago, archaeological evidence increasingly documents specialized bone tools. More diverse projectile technologies expanded use of ornaments, and growing regional variation among Homo sapiens populations. Scholars continue debating exactly how much of this innovation predates Neanderthal disappearance or develops afterward. Nevertheless, cultural adaptability appears to accelerate within surviving Homo sapiens groups, potentially allowing faster responses to rapidly changing ecological conditions. One particularly fascinating possibility is that extinction does not always involve complete replacement. Ancient DNA demonstrates that Neanderthals contribute genetic material to future generations of Homo sapiens. Some individuals, therefore, do not simply vanish. Their descendants become absorbed into expanding modern human populations. In this sense, extinction is partially transformed into assimilation. Entire communities disappear as distinct cultural and biological groups, while fragments of their ancestry continue living within another branch of humanity. This perspective changes the emotional character of the story. Rather than imagining every Neanderthal lineage ending in isolation, it becomes possible that some families gradually merge with neighboring Homo sapiens communities. Their languages, traditions, and identities may slowly fade, yet portions of their biological heritage survive. The process resembles tributaries joining a larger river. The smaller streams lose their separate names, but continue flowing within the greater current. The Denisovans present an even greater mystery. Their fossil record remains extraordinarily sparse despite their surprisingly widespread genetic legacy. They may survive in parts of Eastern Asia long after disappearing elsewhere, but the archaeological evidence remains incomplete. Entire chapters of their history likely remain buried beneath sediments or lost in tropical environments where bones decay rapidly. Every newly discovered cave in Asia carries the possibility of revealing another fragment of this elusive population. Another factor sometimes overlooked is simple chance. Evolution is not always governed by superiority. Random events repeatedly influence survival. A prolonged drought affecting one valley but not another. A successful migration reaching an unoccupied refuge. A volcanic eruption disrupting one region while sparing neighboring territories. Small populations are especially vulnerable to such unpredictable events because they possess fewer opportunities for recovery after unexpected losses. What survives in the record therefore suggests a mosaic rather than a single explanation. Climate creates instability. Small population size increases vulnerability. Competition influences access to resources. Genetic isolation reduces resilience. Disease may occasionally contribute. Interbreeding absorbs some individuals into expanding Homo sapiens populations. Random events amplify existing weaknesses. Together, these interacting forces gradually narrow humanity's extraordinary diversity until only one branch remains. The disappearance of the lost branches is not a tale of failure. Neanderthals endure for hundreds of thousands of years across some of the harshest environments inhabited by any human population. Denisovans successfully adapt to landscapes ranging from Siberian forests to high mountain plateaus. Other ancient human groups survive on isolated islands under unique ecological conditions. Their extinction reflects the immense complexity of evolution, rather than any simple measure of intelligence or worth. In the end, the greatest lesson may be that survival is never guaranteed even for remarkably capable populations. History often remembers only the lineage that remains, yet beneath that apparent victory lies a far older world in which many different kinds of humans once walked the same valleys, watched the same changing skies, and unknowingly stood together at the fragile crossroads of our shared evolutionary past. Long after the last living Neanderthal disappears and the Denisovans fade from the landscapes they once inhabited, the Earth continues preserving their story in unexpected places. The evidence does not survive in a single spectacular city buried beneath desert sands or in an untouched royal tomb waiting to be opened. Instead, it remains scattered across thousands of kilometers, hidden inside caves, riverbanks, ancient lake sediments, mountain shelters, and windswept plains. Every site contributes only a fragment, yet together they reveal one of the most remarkable reconstructions in modern science. The lost branch of humanity is recovered not from one discovery, but from hundreds, each illuminating a different corner of an almost forgotten world. Across southwestern France, northern Spain, Belgium, Croatia, Germany, and Italy, limestone caves preserve some of the richest records of Neanderthal life. Layer upon layer of sediment accumulates over tens of thousands of years, sealing fireplaces, stone tools, butchered animal bones, and occasionally the remains of the people themselves. These caves become natural archives protecting delicate evidence from rain, sunlight, and erosion long after open-air camps have vanished without trace. Each excavation resembles an investigation conducted in slow motion. Archaeologists remove sediment centimetre by centimetre, carefully documenting the position of every artifact before lifting it from the ground. A single mistake can erase information that has survived for 50,000 years. Modern excavations therefore proceed with extraordinary patience. Soil is sifted through fine screens to recover tiny fragments of bone seeds, charcoal and stone flakes that earlier generations of researchers might have overlooked completely. One remarkable aspect of these sites is their consistency. Similar patterns appear across enormous distances. Hearths occupy protected areas within caves. Stoneworking debris accumulates where tools are manufactured or repaired. Animal bones bearing cut marks cluster around places where carcasses are processed. These repeated arrangements suggest that ancient communities organize living spaces according to practical routines shared across generations. The details vary from region to region, but the underlying logic remains strikingly familiar. In the limestone valleys of France, archaeologists uncover evidence that Neanderthal groups repeatedly return to the same shelters over thousands of years. Some caves contain dozens of occupation layers, each separated by periods when changing climates or shifting animal migrations temporarily alter settlement patterns. Rather than permanent homes, these locations function as seasonal anchors within much larger territories. Families come and go as the landscape itself transforms around them. Farther east, discoveries in the mountains of Croatia preserve exceptionally important fossil remains. Here, some of the earliest successful recoveries of Neanderthal DNA become possible because cool cave conditions protect fragile genetic material far better than exposed environments. Bones that initially seem valuable only for anatomical study eventually revolutionize the understanding of ancient human relationships once genomic technologies mature decades later. The Iberian Peninsula provides another crucial chapter in the story. Evidence suggests that some of the last surviving Neanderthal populations may persist in parts of southern Spain after disappearing from much of the rest of Europe. Dating these final occupations remains technically challenging, and scholars continue debating the precise chronology. Nevertheless, the possibility that isolated communities survive for thousands of years within favourable climatic refuges highlights how uneven extinction can be. A population may vanish from one region while continuing elsewhere for many generations. Moving eastward into the Altai Mountains of southern Siberia, the archaeological landscape changes dramatically. Here lies Denisova Cave, outwardly modest compared with many famous prehistoric sites. Few visitors would guess that this quiet cave overlooking a forested valley contains evidence capable of reshaping humanity's evolutionary tree. Excavations recover stone tools, ornaments, animal remains, and a remarkably small number of human fossils. Yet these few fragments prove among the most scientifically significant ever discovered. The cave itself preserves occupations spanning hundreds of thousands of years. Different human populations return repeatedly as climates fluctuate and ecosystems change. At various times, Neanderthals inhabit the shelter. Denisovans occupy it during other periods. Modern humans eventually appear as well. Few archaeological sites anywhere in the world preserve evidence for so many branches of humanity, using the same location across immense stretches of time. The cave becomes less a home for one people than a crossroads where different chapters of human evolution quietly overlap. Not every important discovery comes from caves. River terraces across Europe yield stone tools and fossil fragments, exposed by erosion or human construction. Ancient lake margins preserve footprints pressed into soft mud before hardening into stone. In England, remarkable fossilized footprints reveal the movements of an ancient human group, crossing coastal sediments nearly 1 million years ago. Although these early people belong to much older populations than the Neanderthals or Denisovans, such discoveries emphasize how rarely fleeting moments survive within the geological record. The Middle East occupies a particularly significant position because it serves repeatedly as a meeting ground between continents. Caves in present-day Israel preserve alternating occupations by Neanderthals and early Homo sapiens. These sites suggest that the region functions as a dynamic frontier where expanding populations encounter one another during different climatic periods. Exactly how often direct interaction occurs remains uncertain, but geography alone makes repeated contact highly plausible. In Central Asia, archaeological evidence continues growing with each passing decade. High-altitude caves, mountain valleys, and open-air sites increasingly reveal that ancient human populations exploit environments once thought too challenging for prolonged occupation. The discovery of Denisovan-related ancestry, contributing to modern Tibetan populations, further strengthens the importance of these mountainous landscapes. What once appears peripheral gradually becomes central to understanding human adaptation. Tropical Asia presents an entirely different challenge. Warm temperatures, heavy rainfall, and acidic soils rapidly destroy bone. As a result, archaeologists often recover stone tools without associated human fossils, making it difficult to identify exactly which populations produced them. Ancient DNA extracted from sediments and improved dating techniques are beginning to fill some of these gaps, but vast regions remain poorly understood. Entire populations may have lived and disappeared here without leaving recognizable skeletons. Even beneath the sea, hidden evidence continues waiting. During periods of lower sea level, many ancient coastlines lie dozens of kilometers farther from today's shores. These coastal environments are attractive to prehistoric communities because they offer abundant food, fresh water, and transportation routes. When glaciers melt after the last ice age, rising oceans gradually flood these settlements. Modern underwater archaeology has only begun exploring these submerged landscapes, suggesting that significant portions of humanity's early history remain inaccessible beneath coastal waters. Perhaps the most remarkable lesson emerging from these scattered sites is how incomplete the map still is. Every decade brings discoveries from regions once considered unimportant. A single tooth recovered from an overlooked cave, microscopic traces of DNA preserved in ancient soil, or improved dating methods applied to long-known fossils can overturn decades of accepted interpretation. Human evolution is not a finished story awaiting summary. It remains an active investigation whose conclusions continue evolving as new evidence emerges. The lost branch of humanity is therefore not confined to one continent or one famous excavation. Its traces stretch from Atlantic coastlines to Siberian forests, from Mediterranean caves to Himalayan plateaus, from drowned coastal plains to isolated islands in Southeast Asia. Together, these scattered fragments form a vast archaeological constellation. Individually, they appear small, almost insignificant. Viewed collectively, they illuminate the remarkable age when many different kinds of humans shared the earth before all but one quietly disappeared into the deep silence of prehistory. For much of the 20th century, the story of human evolution advances at a measured pace. Each new fossil is celebrated, each excavation adds another piece to the puzzle, and every revised timeline slightly reshapes scientific understanding. Yet the basic framework remains relatively stable. Researchers compare bones, classify stone tools, and reconstruct ancient environments, using methods that steadily improve but remain fundamentally familiar. Then, almost unexpectedly, a technological revolution begins. It does not happen in the field with larger excavations or more dramatic discoveries. Instead, it takes place inside laboratories, where advances in molecular biology, computing chemistry, and imaging allow scientists to ask questions that previous generations could scarcely imagine. The emergence of ancient DNA research marks only the beginning. Soon afterward, improvements in high-throughput genetic sequencing dramatically increase the amount of information recoverable from even tiny fossil fragments. Samples once considered too degraded to analyze suddenly become valuable. Instead of reading isolated portions of a genome, researchers reconstruct increasingly complete genetic profiles. Computers capable of processing enormous datasets compare millions of genetic markers, simultaneously revealing subtle relationships invisible through anatomical study alone. Every improvement produces unexpected consequences. Fossils collected decades earlier, long stored in museum drawers, are re-examined using modern techniques. Bones previously classified according to external appearance now undergo genetic analysis, sometimes confirming earlier conclusions but occasionally overturning them entirely. Entire museum collections become fresh sources of discovery without a single new excavation taking place. Dating methods undergo a similar transformation. Radiocarbon dating remains enormously valuable, but possesses natural limitations beyond roughly 50,000 years. New approaches refine the chronology of older archaeological sites by measuring trapped electrons within minerals, radioactive isotopes inside sediments, or subtle chemical changes occurring over immense spans of time. As dating becomes more precise, researchers recognize that events once thought simultaneous are actually separated by thousands of years, while others believed unrelated prove surprisingly close in time. Microscopic analysis also enters a new era. Powerful scanning electron microscopes reveal tiny wear patterns left on stone tools after cutting meat-scraping hides or processing plants. Residues trapped within microscopic cracks preserve traces of blood, proteins, starch, grains, and plant fibers. Archaeologists no longer classify artifacts solely by shape. They increasingly understand how tools are actually used in everyday life. Dental calculus. The hardened plaque that accumulates on teeth emerges as another unexpected archive. For generations, dentists regard it merely as an unpleasant deposit requiring removal. To archaeologists, however, it becomes a time capsule, preserving fragments of ancient diets, environmental particles, smoke from campfires, microorganisms living inside prehistoric mouths, and even tiny remnants of medicinal plants. A single tooth may reveal what an individual eats, which environments they inhabit, and aspects of their general health. Information once considered permanently lost now survives within deposits measured in millimeters. Stable isotope analysis opens yet another window into vanished lives. Different foods leave distinct chemical signatures inside bones and teeth. By measuring ratios of particular isotopes, scientists estimate whether ancient populations rely heavily upon meat, freshwater, fish, marine resources, or plant foods. Similar methods reveal seasonal movement between environments or identify individuals who grow up in one region before spending adulthood elsewhere. Human mobility, once inferred only indirectly, becomes increasingly visible through chemistry itself. Perhaps one of the most remarkable innovations is the recovery of environmental DNA from sediments. Traditionally, archaeologists depend upon visible bones to identify ancient occupants of a site. Now, microscopic genetic fragments preserved within cave soils reveal that humans, animals, and plants once occupy locations even when skeletal remains have disappeared completely. A cave floor becomes a biological archive capable of recording visitors who leave almost no other trace behind. This approach proves especially valuable in regions where fossil preservation is poor. Tropical climates rapidly destroy bones, but under favorable conditions, tiny fragments of DNA sometimes remain protected within sediments. Scholars still debate the limits of these techniques, and contamination remains an important concern, yet the possibilities continue expanding. Entire landscapes, once considered archaeologically silent, begin yielding molecular evidence of ancient occupation. Artificial intelligence and advanced computational modeling also transform the field. Programs compare enormous numbers of fossil measurements far more rapidly than manual analysis ever permits. Digital reconstructions restore crushed skulls to their original shapes using mathematical modeling. Three-dimensional scanning allows researchers across the world to examine identical virtual fossils without transporting fragile originals between museums. Collaboration accelerates as digital archives replace geographic isolation. Climate science contributes equally important insights. High-resolution ice cores drilled from Greenland and Antarctica preserve detailed records of ancient atmospheric conditions extending back hundreds of thousands of years. Ocean sediments, cave formations, and fossil pollen reconstruct regional climates with increasing accuracy. Archaeologists now compare human occupation patterns directly against environmental fluctuations, revealing complex relationships between population movements and changing ecosystems. One particularly intriguing development involves proteins rather than DNA. Ancient proteins often survive longer than genetic material because they are chemically more stable. The emerging field of paleoproteomics analyzes these preserved molecules to identify species relationships even when DNA has completely disappeared. A fossil too old or too degraded for genetic sequencing may still preserve proteins capable of revealing its place within the human family tree. This technique has already helped classify enigmatic fossils from regions where DNA recovery proves impossible. As scientific tools become more sophisticated, certainty does not always increase. Instead, researchers frequently uncover greater complexity. Populations once assumed genetically uniform reveal unexpected diversity. Migration routes multiply. Hidden episodes of interbreeding emerge. Some fossils resist classification despite every available technology. Rather than simplifying the story, modern science repeatedly demonstrates that human evolution is even more intricate than previously imagined. The evidence remains incomplete, and scientists openly acknowledge its limitations. Ancient DNA survives primarily in cooler environments, creating geographic biases within available datasets. Fossils remain extraordinarily rare. Many regions of Africa, Southeast Asia, and tropical climates are still underrepresented compared with Europe. Every conclusion therefore reflects the evidence currently available rather than the entirety of ancient reality. Future discoveries may yet alter even today's most widely accepted interpretations. What survives in the record nevertheless points toward an extraordinary conclusion. Human evolution is no longer reconstructed through isolated lines of evidence. Genetics, archaeology, geology, chemistry, climate science, anatomy, computer modeling, and molecular biology now converge to illuminate the same ancient story from different directions. Each discipline contributes unique insights while correcting the limitations of the others. The result is perhaps the most interdisciplinary investigation ever undertaken into humanity's origins. Ironically, the more advanced modern science becomes, the more vividly it restores the lives of people who leave behind no written words. Tiny molecules hidden inside bones, microscopic particles trapped within teeth, invisible traces preserved in ancient soil, and digital reconstructions built from damaged fossils collectively allow researchers to glimpse worlds that vanished tens of thousands of years ago. The lost branches of humanity remain silent, yet the technologies of the 21st century have learned to hear echoes carried not by memory, but by the smallest surviving fragments of the ancient past. Long before archaeology becomes a science, people attempt to explain the strange bones emerging from caves and riverbanks, through stories rather than evidence. A massive skull found in a rocky hillside becomes the remains of a giant defeated in an ancient battle. Enormous fossilized teeth are attributed to dragons, monsters, or forgotten heroes. Across continents, legends arise to explain mysterious traces left by a past that no living community can fully remember. These traditions are not deliberate attempts to deceive. They are natural human responses to discoveries that seem too extraordinary to fit ordinary experience. As modern research uncovers the existence of multiple human species living alongside one another, an intriguing question occasionally emerges. Could some ancient myths preserve distant echoes of encounters between different branches of humanity? The idea is undeniably fascinating. If Homo sapiens and Neanderthals share parts of Europe and Western Asia for thousands of years, and if Denisovans occupy vast regions farther east, might faint cultural memories survive long after the last of these populations disappear, the possibility has inspired books, documentaries, and countless discussions. Yet it also demands careful restraint. Oral traditions are remarkably durable, capable of preserving historical information across many generations. Indigenous communities around the world maintain stories that accurately describe volcanic eruptions, coastal flooding, or changing landscapes occurring thousands of years before written records. Such examples demonstrate that collective memory can endure far longer than many researchers once believed. Even so, there are practical limits. Neanderthals disappear approximately 40,000 years ago, while Denisovans likely vanish around a similar general period, though the exact timing remains uncertain. Maintaining an unbroken oral tradition over such immense spans of time would be unprecedented. Languages change beyond recognition in only a few thousand years. Entire cultures rise, transform, and disappear repeatedly. Direct memories of encounters with extinct human populations almost certainly fade long before recorded history begins. Nevertheless, some scholars suggest that later myths may preserve indirect reflections of inherited impressions rather than literal historical accounts. Throughout Europe and parts of Western Asia, folklore often describes mysterious wild people inhabiting forests or mountains beyond settled lands. These beings are portrayed in many different ways. Sometimes they appear frightening and powerful. Elsewhere, they are depicted as shy, elusive, or surprisingly intelligent. Similar traditions occur in many unrelated cultures, reflecting a widespread tendency to imagine human-like beings existing just beyond familiar territory. It is tempting to connect such stories with prehistoric encounters. Yet mainstream archaeology urges caution. Human societies frequently create myths about neighboring groups, outsiders, spirits, or supernatural beings without requiring actual contact with extinct human species. Similar narratives emerge independently across cultures because they address common psychological themes rather than shared historical events. The resemblance between folklore and prehistoric possibilities does not necessarily imply direct continuity. The same caution applies to legends of giants. Throughout history, people discovering unusually large fossil bones often attribute them to enormous ancient humans. Before the development of paleontology, the remains of mammoths, mastodons, extinct rhinoceroses, and other Ice Age mammals are regularly interpreted as evidence of gigantic people or legendary creatures. Such misunderstandings are understandable given the available knowledge. Large bones demand explanation, and myth provides one long before science offers another. In parts of Asia, stories describing mysterious mountain dwellers occasionally attract renewed attention after the discovery of Denisovan fossils and the realization that these ancient people inhabit high-altitude environments. Could traditions involving hidden mountain beings preserve distant echoes of Denisovans? The evidence remains incomplete, and no direct connection has been demonstrated. Most anthropologists regard such ideas as interesting possibilities, worthy of discussion but unsupported as historical conclusions. Modern fascination with creatures such as Bigfoot or the Yeti has also encouraged speculation linking legendary beings to surviving populations of ancient humans. Popular culture often imagines isolated Neanderthals or other archaic humans secretly inhabiting remote forests or mountain ranges into the present day. Scientific evidence, however, provides no support for this scenario. Extensive genetic research, archaeology, and paleontology indicate that no non-sapiens human populations disappear tens of thousands of years ago. No verified fossils, DNA samples, or living individuals suggest otherwise. This distinction between evidence and imagination is important, because the true story of humanity's lost branches is already extraordinary, without requiring unsupported additions. The existence of Neanderthals, Denisovans, Homo floresiensis, Homo luzonensis, and other ancient populations once seems almost unbelievable. Yet each is established through carefully examined fossils, genetic analysis, and archaeological context. Science advances precisely because it separates what is demonstrable from what remains speculative. At the same time, myths retain genuine value for understanding the human mind. They reveal how different societies interpret landscapes, unusual discoveries, and the unknown. Caves become entrances to other worlds. Ancient forests shelter mysterious inhabitants. High mountains conceal beings beyond ordinary experience. Such narratives express universal human curiosity about hidden histories and forgotten neighbours. In that sense, they reflect the same impulse that drives archaeology itself, the desire to understand those who come before. Interestingly, some archaeological discoveries have inspired entirely new myths within modern culture. When the diminutive human species from Flores is announced, newspapers quickly adopt nicknames such as the Hobbit, borrowing imagery from modern literature to help audiences visualize unfamiliar fossils. Denisovans, known initially from only a finger bone and a few teeth, are imagined in countless artistic reconstructions despite the limited anatomical evidence available. Even contemporary societies create stories around fragmentary discoveries, demonstrating that imagination continues accompanying scientific investigation. Scholars still debate how best to communicate uncertainty without diminishing wonder. A careful scientist may explain that evidence neither confirms nor rules out certain possibilities, while public discussion often favors simple and dramatic conclusions. Maintaining the distinction between evidence and speculation becomes increasingly important as discoveries capture global attention. The lost branches of humanity deserve to be understood through the remarkable evidence they genuinely provide rather than through unsupported embellishment. Perhaps the greatest lesson offered by ancient myths is not that they preserve literal memories of extinct humans, but that they remind us how easily forgotten the distant past can become. Entire populations once inhabit continents for hundreds of thousands of years before disappearing so completely that later civilizations possess no conscious awareness of their existence. Mountains remain rivers, continue flowing, and caves endure, yet the people themselves vanish from memory until science gradually uncovers them again. In this way, archaeology and mythology meet at an unexpected point. Both acknowledge that the world is older, stranger, and more layered than it first appears. Myth fills the silence with stories shaped by imagination. Science fills it with evidence assembled piece by piece, across generations of careful research. Together they reveal something deeply human. Whenever confronted with traces of an unfamiliar past, people seek meaning. Sometimes that meaning takes the form of legend. Sometimes it emerges through fossils, DNA, and patient investigation. Both begin with the same enduring realization that beneath the ordinary landscape lies another world waiting to be understood. Although the last recognizable Neanderthal or Denisovan dies tens of thousands of years ago, their story does not truly end there. Extinction suggests finality, an absolute break between the past and the present. Yet one of the most remarkable discoveries of modern genetics reveals that disappearance is sometimes far more complicated. Entire populations may vanish from the Earth, while fragments of their biological inheritance continue traveling quietly through countless future generations. The lost branch of humanity has not simply become a subject for museums. In subtle but measurable ways, it still exists within the people living today. When researchers first identify Neanderthal DNA in modern populations outside Africa, the discovery raises immediate questions. If ancient interbreeding occurs only rarely, why do these inherited sequences persist for so many thousands of years? Evolution provides the answer. Most inherited genetic variants gradually disappear unless they are either neutral or beneficial. Harmful changes tend to be removed over time because individuals carrying them leave fewer descendants. Beneficial variants, however, may spread through growing populations if they improve survival or reproductive success. Some Neanderthal genes appear to do exactly that. As Homo sapiens expands from Africa into unfamiliar regions of Europe and Asia, these newcomers encounter climates, plants, animals and microorganisms unlike those experienced by their earlier ancestors. Neanderthals have already lived within these environments for hundreds of thousands of years. During that immense span of time, natural selection shapes genetic adaptations suited to local conditions. When interbreeding occurs, certain useful variants enter the expanding Homo sapiens population. Among the most significant inherited traits involve the immune system. Ancient pathogens evolve alongside Neanderthal populations over many millennia. Genetic variants improving resistance to these microorganisms become increasingly common among them. When those same variants pass into modern humans, they may provide valuable protection against diseases encountered in Eurasia. Rather than developing entirely new adaptations from the beginning, Homo sapiens sometimes acquires genetic shortcuts already tested through countless generations of evolution. Researchers have identified several inherited Neanderthal sequences associated with immune responses, inflammation, and the recognition of invading microbes. The exact biological effects remain an active area of research, and scholars still debate how strongly particular genes influence overall health. Nevertheless, the broader pattern is well supported. Ancient interbreeding contributes directly to aspects of immune function still operating within millions of people today. The relationship, however, is far from simple. Traits beneficial during the Ice Age are not necessarily advantageous in modern environments. A stronger inflammatory response may help prehistoric populations combat dangerous infections. Yet in contemporary societies, it can also increase susceptibility to allergies or autoimmune disorders. Evolution never anticipates future lifestyles. It responds only to immediate conditions. Genes once essential for survival may become less useful after dramatic changes in diet, medicine, sanitation, and life expectancy. Skin and hair biology provide another fascinating example. As modern humans migrate into northern latitudes with lower levels of sunlight inherited, Neanderthal variants affecting skin physiology and hair characteristics may prove advantageous. These adaptations continue interacting with countless other genes accumulated throughout later human history, producing subtle influences rather than dramatic transformations. No modern individual resembles a Neanderthal simply because of these inherited fragments. Instead, ancient DNA contributes tiny pieces to an enormously complex genetic mosaic. The Denisovan legacy proves equally remarkable, particularly in Asia and Oceania. populations in Papua New Guinea, Australia, and parts of Southeast Asia possess significantly more Denisovan ancestry than most other modern groups. This pattern indicates repeated interactions between Denisovans and expanding Homo sapiens populations as people move through Eastern Asia toward the islands of the Pacific. Perhaps the best-known example involves adaptation to life at extreme altitude. The Tibetan Plateau rises more than 4,000 meters above sea level, where oxygen availability is substantially reduced. Most people ascending rapidly to such elevations experience severe physiological stress. Yet Tibetan populations display remarkable adaptations, allowing efficient oxygen use without the unusually thick blood that develops in many lowland individuals. Genetic studies reveal that one important variant associated with this adaptation is likely inherited from Denisovan ancestors. Thousands of years after Denisovan populations disappear, one of their evolutionary innovations continues helping modern communities thrive in one of the world's most demanding environments. It is a striking reminder that extinction does not always erase every contribution a population makes to future history. Ancient DNA has also revealed something unexpected about the complexity of human ancestry. Rather than occurring through a single episode of interbreeding contact between Homo sapiens and archaic populations, appears to happen multiple times across different regions and periods. Some inherited genetic fragments are shared widely across Eurasia, while others occur only in specific populations, reflecting localized encounters whose details remain lost. The evidence remains incomplete because many ancient genomes have yet to be recovered. Tropical climates preserve DNA, poorly leaving large portions of Africa, South Asia and Southeast Asia underrepresented. Scholars continue debating whether additional extinct human populations contribute genetic material to modern people. Intriguing signals within some African genomes hint at possible ancestry from unidentified archaic populations that have not yet been discovered through fossils. If confirmed, such findings would further expand the already complex picture of human evolution. Modern medicine has become increasingly interested in these ancient genetic inheritances. Researchers investigate whether Neanderthal-derived variants influence responses to infectious diseases, metabolic conditions, sleep patterns, pain perception, or even certain aspects of neurological function. Many studies identify statistical associations, though interpreting these relationships remains challenging because human biology results from interactions among thousands of genes alongside environmental influences. No single inherited sequence determines complex behaviors or personalities. One lesson emerges consistently from this research. Humanity's past is not neatly divided into separate categories of extinct and surviving species. Instead, evolution resembles overlapping currents within a vast river. Some branches end completely, others merge before disappearing as distinct populations. Still others leave small but lasting contributions that continue flowing through future generations long after their original identities fade. This realization has profound implications beyond biology. It challenges older narratives portraying modern humans as isolated victors, replacing every earlier population without interaction. Instead, the surviving branch carries within itself traces of those once thought entirely lost. The boundary between extinction and survival becomes less absolute than previously imagined. Looking into a mirror today, no one can identify inherited Neanderthal or Denisovan ancestry simply by appearance. These ancient genetic fragments are dispersed unevenly throughout populations and contribute only a tiny proportion of any individual's genome. Yet they remain genuine biological connections linking the present to people who walk Ice Age landscapes tens of thousands of years ago. The lost branch of humanity therefore continues accompanying modern civilization in invisible ways. every scientific breakthrough revealing another inherited adaptation, another ancient encounter, or another unexpected genetic connection, reminds us that history is not confined to books or fossils. It is carried inside living cells passed quietly from parent to child across thousands of generations. Long after the final campfire of the last Neanderthal grows cold and the final Denisovan settlement disappears into silence, pieces of their story remain alive within the only surviving branch of humanity, ensuring that they are never completely gone. As each new fossil is uncovered and every ancient genome is decoded, one realization grows steadily more difficult to ignore. The greatest discovery is not simply that other kinds of humans once exist. It is that the idea of what it means to be human has been quietly transformed. The old image of humanity standing apart from every other form of life alone and fundamentally unique throughout prehistory has given way to something far more intricate. The surviving branch is no longer viewed as the sole protagonist in an otherwise empty landscape. Instead, it becomes the final chapter of a much larger family story. For generations, intelligence is often treated as a single dividing line. The assumption seems straightforward. Modern humans possess advanced language, symbolic thought, complex planning and creativity, while extinct relatives are imagined as occupying a simpler world governed mainly by instinct. Yet the archaeological evidence accumulated during the past several decades steadily erodes this comfortable distinction. Neanderthals manufacture sophisticated stone tools that require careful preparation and long-term planning. They select particular kinds of rock transport high-quality materials across considerable distances and repeatedly refine techniques over thousands of years. Their methods change gradually through time, demonstrating that technological traditions evolve rather than remaining frozen. Such continuity implies teaching, learning, and cultural transmission, extending across generations. The same pattern appears in their ability to exploit diverse environments. Few species occupy landscapes ranging from Mediterranean woodlands to the frozen plains of Ice Age northern Europe for hundreds of thousands of years. Achieving such geographic flexibility requires far more than physical strength. It demands detailed environmental knowledge, social cooperation, and the capacity to adjust behavior as conditions change. Evidence suggesting symbolic behavior continues to provoke lively discussion. Archaeologists have recovered pieces of red and yellow mineral pigments from several Neanderthal sites, some showing clear signs of deliberate scraping or grinding. Pigments may have been used to color hides, decorate objects, or perhaps even mark the human body. The precise purpose remains uncertain, because the archaeological record rarely preserves the organic materials to which these pigments might once have been applied. Similarly, eagle talons bearing carefully placed cut marks have been discovered at several sites. These modifications strongly suggest that the claws were intentionally removed rather than left attached to the animal. Some researchers interpret them as ornaments suspended from cords or attached to clothing. Others urge caution, arguing that practical uses cannot always be excluded. The evidence remains incomplete, yet such discoveries consistently point toward behaviors extending beyond immediate survival. Burial practices raise equally important questions. At several locations, human remains appear to have been deliberately placed within prepared depressions before being covered with sediment. In one famous cave, pollen found near a Neanderthal skeleton initially inspires the idea that flowers accompany the burial. Later studies suggest alternative explanations involving burrowing animals or natural processes, illustrating how scientific interpretations continue evolving as methods improve. Even so, multiple sites preserve indications that at least some bodies receive treatment differing from ordinary abandonment. Whether these practices reflect spiritual beliefs, social customs, emotional attachment, or practical concerns remains impossible to determine with certainty. Archaeology can identify patterns of behavior, but it cannot directly recover thoughts or intentions. Scholars therefore distinguish carefully between observable evidence and broader interpretations. Nevertheless, the repeated appearance of deliberate body placement suggests that death holds significance extending beyond simple disposal. Language presents another enduring mystery. Spoken words vanish almost instantly after they are uttered, leaving no direct fossil evidence. Yet anatomy offers valuable clues. Neanderthals possess ear structures capable of detecting frequencies similar to those important for modern speech. Their hyoid bones involved in supporting the tongue and muscles of the throat closely resemble those of Homo sapiens. Genetic studies reveal that they carry versions of genes associated with speech and language development, including the well-known FOXP2 gene. Although this gene alone does not create language, none of these discoveries proves that Neanderthals speak exactly as modern humans do. Language involves far more than anatomy or genetics. It depends upon complex neurological organization, social learning, and cultural transmission. Still, the accumulating evidence increasingly supports the possibility that sophisticated vocal communication exists among multiple human populations, rather than emerging suddenly within Homo sapiens alone. Even the concept of intelligence itself has become more nuanced. Intelligence is no longer viewed as a single measurable quantity, placing species along a simple ladder of progress. Instead, researchers increasingly recognize many forms of cognitive adaptation. Navigating frozen landscapes, memorizing seasonal migrations, manufacturing complex tools, coordinating cooperative hunts, caring for injured companions, and transmitting survival knowledge across generations all require remarkable mental abilities. Different environments reward different forms of expertise. The survival of Neanderthals for more than 400,000 years offers compelling evidence of this reality. Few large mammals persist successfully through repeated climatic upheavals over such immense periods. Their longevity demonstrates resilience rather than inadequacy. If they eventually disappear, it is not because they fail to become human enough. Rather, they represent one successful evolutionary strategy among several ultimately overtaken through a combination of environmental change, demographic pressures, genetic factors, and historical circumstance. This perspective also reshapes the understanding of Homo sapiens. The surviving branch appears less like an inevitable pinnacle of evolution and more like one fortunate lineage navigating an extraordinarily complex series of challenges. Success depends upon flexibility, cooperation, innovation, and sometimes simple chance. Had climatic conditions unfolded differently, had migration routes shifted, or had population sizes varied only slightly, the outcome might not have been identical. Evolution offers opportunities, not guarantees. Scholars still debate the extent to which uniquely modern behaviors emerge gradually or rapidly. Some argue for a slow accumulation of cultural complexity stretching deep into prehistory. Others emphasize periods of accelerated innovation associated with expanding social networks and demographic growth. Both perspectives acknowledge that humanity's defining characteristics evolve over long timescales, rather than appearing all at once. Perhaps the most significant consequence of these discoveries is philosophical rather than biological. The boundary separating us from them becomes increasingly difficult to draw. The more scientists learn about extinct human relatives, the more familiar they appear. They adapt, creatively cooperate socially, care for one another, and leave subtle traces of symbolic expression. They experience childhood injury, aging, and death beneath the same changing skies that still arch above the modern world. Standing at the edge of this expanded understanding, humanity begins to recognize itself not as an isolated exception, but as the final surviving member of an ancient and remarkably diverse family. Every new discovery narrows the emotional distance separating the present from those forgotten branches. Their lives are no longer viewed merely as evolutionary experiments ending in failure. Instead, they become chapters within the same long story, a shared inheritance stretching across hundreds of thousands of years, reminding us that being human has always meant belonging to something far larger than a single surviving species. The search for humanity's lost branches is far from over. In many ways, it has only entered its most revealing chapter. Every year, archaeologists uncover caves that have never been systematically explored, recover fossils from landscapes once considered unlikely, to preserve ancient remains and apply new technologies to specimens that have rested in museum collections for generations. What once appears to be a nearly complete story repeatedly proves to be only another draft revised whenever the Earth yields another carefully hidden fragment of its immense memory. One of the most striking lessons emerging from recent decades is how often expectations have been overturned. Before the discovery of Denisovan DNA, few researchers imagined that an entire human population could remain unknown despite decades of excavation. Before the identification of Homo floresiensis, the idea that a small-bodied human species survives on an isolated Indonesian island until relatively recent prehistory seems improbable to many specialists. Before ancient genomes become readable, few anticipate that modern people carry measurable genetic inheritance from extinct human relatives. These discoveries encourage scientific humility. Every conclusion remains provisional, built upon the evidence currently available, rather than upon absolute certainty. The fossil record is extraordinarily incomplete. Most ancient humans leave no recoverable remains. Entire populations may live in environments where bone preservation is exceptionally poor. Tropical forests, acidic soils, fluctuating water tables, and countless geological processes erase evidence long before archaeologists have the opportunity to search for it. Africa, the birthplace of our species, illustrates this challenge particularly well. Although extraordinary discoveries continue to emerge from eastern and southern Africa, vast regions remain only lightly explored. Genetic studies occasionally identify patterns suggesting that ancient Homo sapiens may have interacted with other archaic human populations whose fossils have not yet been conclusively identified. Scholars still debate these findings and the evidence remains incomplete, but the possibility itself is remarkable. The human family tree may contain branches that are currently known only through faint genetic echoes. Southeast Asia presents another frontier. Dense tropical vegetation, rapid decomposition, and complex geological histories make archaeological research especially demanding. Yet each new excavation continues to reveal surprising diversity. Additional human populations may once have occupied islands now separated by rising seas after the end of the last ice age. Some may never be represented by complete skeletons. Instead, they may first emerge through fragments of ancient DNA, preserved in cave sediments, or through isolated teeth and bone fragments that initially appear insignificant. The seabed itself represents one of the least explored chapters of human evolution. During the coldest phases of the Ice Age, sea levels stand dramatically lower than today. Vast coastal plains connect islands, expose new migration corridors, and create productive environments rich in marine life. Ancient communities almost certainly establish camps along these shorelines, taking advantage of abundant food and fresh water. As glaciers melt, however, rising oceans gradually submerge these landscapes beneath tens of meters of water. Modern underwater archaeology has only begun investigating these drowned worlds. Sophisticated sonar mapping, remotely operated vehicles, and underwater excavation techniques are revealing traces of ancient river channels, forests, and possible human activity beneath today's coastlines. Much of the archaeological record may still lie hidden, offshore, preserved beneath marine sediments that have remained undisturbed for thousands of years. Technology continues advancing at remarkable speed. Researchers now recover ancient proteins from fossils too old for DNA analysis. Environmental DNA extracted from sediments is becoming increasingly sensitive, capable of detecting the presence of humans and animals even when no visible remains survive. Artificial intelligence assists in identifying subtle anatomical differences invisible through traditional measurement alone. Three-dimensional imaging allows damaged fossils to be reconstructed digitally without risking physical harm to priceless specimens. Yet perhaps the greatest transformation is not technological, but conceptual. Scientists increasingly approach human evolution as a network rather than a ladder. Earlier generations often search for direct ancestors, leading neatly toward modern humanity. Contemporary research instead emphasizes branching populations, regional diversity, repeated migrations, and occasional interbreeding. The surviving lineage is understood not as the inevitable endpoint of progress, but as one thread woven through a far richer evolutionary tapestry. This perspective encourages a broader understanding of extinction itself. The disappearance of a population does not necessarily erase every aspect of its existence. Technology's behaviors and genetic adaptations may continue influencing later communities. Landscapes shaped by generations of hunting or controlled fire may affect ecosystems long after their creators are gone. Even ideas about cooperation, adaptation, and resilience become part of a much longer human inheritance. Although their precise forms remain impossible to reconstruct fully, the lost branch of humanity also offers a powerful reminder of fragility. From the perspective of deep time, modern civilization occupies only a tiny moment. Agriculture begins roughly 12,000 years ago. Writing appears only a few thousand years later. Industrial society spans scarcely more than 2 centuries. By contrast, Neanderthals inhabit Eurasia for hundreds of thousands of years. Their story alone extends far beyond the entirety of recorded history. Such comparisons place humanity's recent achievements within a much larger temporal landscape. Looking across that immense span, survival appears less permanent than it often seems. Numerous human populations thrive successfully for tens or even hundreds of thousands of years before eventually disappearing. None anticipate extinction as they raise children, gather food, or watch familiar seasons return. Their daily lives are filled with ordinary concerns rather than awareness of historical significance. The same is true of nearly every generation throughout history. What survives in the record suggests that resilience depends upon adaptability more than certainty. The branches that endure longest are those capable of responding to changing climates, shifting ecosystems, unfamiliar neighbors, and unpredictable challenges. Evolution favors flexibility over perfection. Even then, success is never guaranteed. Chance continues shaping outcomes alongside intelligence, cooperation, and innovation. As scientists continue uncovering forgotten chapters of the human story, the boundaries of the known world steadily expand. A cave that appears empty today may tomorrow reveal microscopic traces of DNA. A fossil resting unnoticed in a museum collection may prove to belong to an entirely new population once analytical techniques improve. A submerged valley beneath coastal waters may preserve evidence of migrations never previously imagined. The investigation remains unfinished because the Earth has not yet revealed everything it remembers. Standing in the present, it is tempting to think of ourselves as the culmination of an ancient journey. The deeper the evidence is examined, however, the more balanced that view becomes. Modern humans are indeed the last surviving branch of a once diverse family, but survival alone does not diminish the achievements of those who came before. They endure ice ages, adapt to unfamiliar landscapes, master difficult technologies, care for one another, and leave traces that continue reshaping scientific understanding tens of thousands of years after their disappearance. Their names are unknown. Their languages are forever silent. Their stories survive only in fragments scattered beneath caves, mountains, riverbanks, and ancient sediments. Yet those fragments have transformed humanity's understanding of itself. They reveal that our past is not a simple line, but a forest of forgotten branches, most of them long gone, all of them contributing in some way to the extraordinary history of being human. Word count 101. The rhythm of this story now begins to slow. Beyond the final fossil and the last strand of ancient DNA lies something even larger than discovery itself. There is the quiet persistence of time measured not in years or centuries, but in landscapes patiently changing beneath open skies. Mountains rise and wear away. Rivers alter their courses. Forests spread across abandoned valleys before retreating once more. Through all of these transformations, generations come and go, each believing its own world to be familiar, rarely imagining how completely it will one day vanish. The lost branches of humanity remind us that survival is never guaranteed, yet disappearance does not always mean oblivion. A fragment of bone resting in a cave can wait 40,000 years before telling its story. A tiny sequence of DNA hidden within living cells can carry the memory of an ancient encounter across countless generations. Even silence can preserve history, provided someone eventually learns how to listen. Perhaps that is the greatest lesson hidden within the deep past. Humanity has never walked alone. Long before kingdoms, languages, cities, or written records, many different kinds of humans shared the same rivers, climbed the same mountains, watched the same migrating herds, and gathered around the warmth of evening fires beneath stars that remain unchanged today. Their worlds disappeared so gradually that none could have recognized the ending while they were living through it. Modern science has not solved every mystery they leave behind. New discoveries will almost certainly challenge some of today's conclusions, just as recent discoveries transform the assumptions of earlier generations. That uncertainty is not a weakness, but a reminder that knowledge continues growing one careful observation at a time. Somewhere beneath an unexplored hillside, inside an unopened cave, or beneath coastal waters that once formed ancient plains, another forgotten chapter may already be waiting. A single tooth, a handful of sediment, or a microscopic fragment of preserved protein could once again reshape the story of humanity's origins. Until then, the lost branches remain quiet companions to our own existence. Though their footsteps have long faded from the earth, their legacy endures in scattered stones, weathered bones, inherited genes, and in the expanding understanding that being human has always meant belonging to a family far older and far more diverse than anyone once imagined. The winds still move across the valleys where they hunted. Rivers continue flowing past caves where their fires once burned. Night still settles over the same mountains that watched generations appear and disappear without leaving names behind. In that enduring landscape, the memory of humanity is never completely lost. It simply waits with extraordinary patience for those willing to uncover it one fragment at a time.